Hello students, this is the second of a two-part video series talking about week 6, which is discrete random variables. We already talked about the basics of discrete random variables in the first video, so go back and watch that if you haven't. Now we're going to be talking about binomial random variables. A binomial random variable is a specific type of discrete random variables that only has two different outcomes. Remember, when rolling a die, you have 6 different outcomes, but with binomial random variables, we're only talking about 2 outcomes. And those 2 outcomes have to be mutually exclusive, which means either one happens or the other happens, but not both. So binomial random variables have to satisfy these 4 requirements: fixed number of times or fixed number of trials. The trials have to be independent, which means one does not affect the other. The trials must have 2 mutually exclusive outcomes, success or failure. There can't be any overlap, and there can't be any other options. And the probability of success has to be fixed. In other words, when I start the trials, I know what the probability of success is, and it doesn't change from trial to trial. Here's some notation that we use for binomial random variables. We use n, italicized n, for the number of trials. We use p for the probability of success, 1 minus p for the probability of failure. And we also use, this got messed up a little bit, and we also use the idea that x, the random variable, has to be in between 0 and n, which makes sense because the number of successes has to be in between 0, it could be that there are 0 successes, and n, which is the total number of trials. You could get 0 successes, you could get all successes, or any number in between. This is a way to write out the binomial probability distribution. This is basically read like this: x is a random variable that follows the binomial distribution with n trials and p as this probability of success. I know that it might seem a little annoying to try to figure out whether a random variable satisfies these 4 requirements. However, there's a reason why we're doing this. If we can identify that a random variable is binomial, then we have a very easy formula that we can use to calculate its probability. If it's binomial, then we can use that probability formula. If it's not binomial, we can't. So the first couple of slides here are going to be talking about, well, is it binomial or is it not? In this first case, a player rolls a pair of fair dice 20 times. It is a binomial experiment. First, we know that it's 20 times. That's a fixed number. Second, we know that the trials are independent because dice are an example of an independent probability outcome here. There are 2 outcomes, either 7 or not 7, because all we're concerned about is the number of 7s rolled. We're not wondering whether it's going to be, a 7 or an 11 or a 4. We're just saying, is it 7 or is it not 7? And we also know that the probability of success is fixed. In other words, the probability of rolling a 7 is 1 out of 6. If you don't believe me, Google it, but trust me, the probability of rolling a 7 on a pair of fair dice is 1 out of 6. For letter B, it is not a binomial experiment. The reason is because it violates the fixed number of trials rule. It says she randomly selects flights until she finds 10. Well, that's the number of successes, but she could have selected 10 flights to find 10. She could have been very lucky, or she could have picked 12, or she could have selected 15, or selected 20. If she just keeps randomly selecting until she finds 10, that is not a fixed number of trials. For letter C, it tells you that 55% of these students are female, but the instructor is randomly selecting 4 students, 1 at a time. So that means once you pick the first student, there's no longer a 55% composition of the class, because now I don't have 30 students anymore. Now I have 29. In a very small sample like this, and I'm trying to pick individuals, that percentage is going to be changing. That percentage is going to be dependent. So we no longer consider these trials to be independent, because once you've picked a female student, the probability of selecting a female student changes. Here's another example of binomial experiments and trying to figure out whether they are in fact binomial. This first one is not, because we don't know the probability of success. So I'm testing this pain reliever, and it could work better for different people. It's true that we could try to find a global percentage or a global efficacy percentage, but we don't have that information. All we know is the number of trials. We don't have a fixed probability of success. For letter B, it says a random sample of 12 students reports how many brothers they have. Well, I don't know about you, but I have 2 brothers. Your answer might be 1, your answer might be 3, your answer might be 0. So this is not a binomial random variable, because we're asking how many brothers they have. This is a discrete random variable, a specific, or not as specific as binomial, but it is not a binomial random variable. And for letter C, this one is actually a binomial random variable because we have a fixed number of trials. We got 10 adults. We have independent trials. because one adult being married doesn't necessarily affect another randomly selected adult being married. There are either two outcomes, either married or not married, and the probability is fixed because it gives it to us. It says the Census Bureau has collected this information. Moving on. All right, this situation tells us that we're looking at 4 different flights randomly selected from May 2008, and the number of on-time flights, which is a random variable x, is recorded. This is a random variable, so we are able to make a probability distribution for it, and then we're going to see if it's binomial. So remember that a tree diagram looks kind of like this. This is a generic tree diagram. Our tree diagram is going to look like this. And it's very colorful because all of the on times are represented in green and all of the lates are represented in red. And if you follow this tree diagram to any one of its branches, you can find the outcomes. So for example, if I follow this tree diagram from here to here to here and then to here, that should be on time, late, late, and on time. If you follow any one of these branches, you should get the outcomes that you're looking for. So what we're able to do is we're able to use this tree diagram and multiply each of the probabilities together to find the probability of this specific outcome. So if I want to find the probability of all of them being on time, I would take 0.79, which is the probability of success, and multiply it by itself 1, 2, 3, 4 times. So the probability of all 4 of them being on time is 0.79 times 0.79 times 0.79 times 0.79. That's 0.79 to the 4th power. This down here, which is on time, late, late, on time, that's 0.79 times 0.21, and that's that is the opposite of being on time. 79% being on time, which means 21% is late. On time is 0.79, late is 0.21, late is 0.21, and on time is 0.79. It's easier to see if I show you in a diagram, so that's what I did here. All of these represent the different possible outcomes of 4 different random flights being selected and how to calculate their probabilities. For example, on time and then late, late, late. That means one of them is on time and 3 of them are late. So what we did here was we made a probability distribution with 0 flights that are on time. That's this one down here. 1 flight that is on time. That's this one, and also this one, and also this one, and also I think that's it. But that's a lot. That's a lot of work to do all these multiplications and add them together. Now, the reason that I showed you that stuff about binomial random variables is because if you know that it's a binomial random variable, you're able to use an easier formula. So let's talk about that. Is this a binomial experiment? Turns out that yes, it is. It follows all 4 of the rules. Is there a fixed number of trials? Yes. There's 4 flights that are selected. Are they independent trials? Yes, because one plane's landing doesn't affect another. Are there 2 disjoint outcomes? Yes, they're either on time or they're late. There's nothing in between. They're not sort of on time or sort of late. Some of my students might argue about that, but no, sorry, students. And then fixed success probability? Yes, because it says up here that 79.0% is the percentage of air carriers that had a percentage that were on time. So it's a binomial experiment. What does that mean? We're able to use specialized formulas. Cue the formula. Well, cue the distribution first. Let's define the distribution. We're saying that x is a random variable that follows the binomial distribution with 4 trials and a probability of success 0.79 or 79%. Once I know that there is a probability of success that's 0.79, once I know the number of trials, and once I know it's binomial, I can use a specialized formula, which looks like this. It might look a little weird, but I'm going to show you in action basically right now. This part of the formula is the combinations formula. It is on your calculator in the math menu under probability. Don't freak out. It's not that bad to use. All right, let's see it in action. If I'm trying to find the probability that all 4 flights are landing on time, that means that there's 4 trials, 4 successes, and the set probability of success of 0.79. That means I'm plugging in all the numbers from n to x to n minus x. All of these numbers just get put in my calculator, and I press enter, and I rounded it to 4 decimal places because that seemed like a nice thing to do. The probability of 2 flights landing on time, that means the probability of 2 successes. So now my success number is 2, my number of total trials is still 4, and my probability has not changed, obviously, because that's one of the conditions for binomial probability. Here's my probability, which is 0.1651. This squiggly equals means I rounded it. Last but not least, the probability of 2 or more flights landing on time, well, that's going to be the probability of successes 2, and also the probability of successes 3, and also the probability of successes 4. You can tell that I did that one time here, plus another time here, plus another time here. And you can also sort through this to figure out that this is the 2 successes, this one is 3 successes, and this one is 4 successes. I added them all together to get 0.9688, which means it is a very good chance that 2 or more flights land on time. All right. Moving on to the next part here, the guiding question from the first video was, what is the probability of flipping a coin 10 times and landing on heads 6 times? This is a binomial experiment, which means that there are a set number of trials, or fixed number of trials, a number of successes, which is given to me, and also a probability of success, which is fixed as well. So what I'm going to do is I'm going to put this into the calculator. 10 choose 6 times 0.5 to the 6th times 0.5 to the 4th. That turns out to be 20.51, which means it's about a 1 in 5 chance that you're going to get 6 heads when flipping a coin 10 times. How interesting. Just to review, these are inequality symbols. It shouldn't take you more than a second to recognize or remember what these mean. Let's talk about binomial probability and how to look at it in action. In this case, 35% of all car-owning households have 3 or more cars. If you have a sample of 20, which means 20 trials, we're looking for the probability that exactly 5 have 3 or more cars. That means the probability of 5 successes in 20 trials with a probability of success 0.35. This is just calculator work. Same thing here, except what I did was I did 4 different calculations and then added them together, kind of like on the previous slide. Check your work, check your math, or check my math, I should say. I definitely did it correctly. All right, going to the example that we talked about before about adults being never married, we're using the same idea of binomial probability again because you're either married or never married. The probability that 2 adults were never married, we're looking for 2 successes. Is that a success? Moving on. We're also looking at 10 different trials and probability of 0.35, so you just plug it into the formula. The probability that less than 2 were never married, well, the reason I showed you that inequalities example in the previous slide is because we're looking for less than 2, which means 1 and 0 are the things that we're looking for. So here's the probability of 1, here's the probability of 0, add them together, bada bing, bada boom. Last but not least, we talk about the mean and standard deviation. Some of the questions on the exams ask you to find the mean and standard deviation of a binomial random variable. It's very simple formulas that you have to use. You don't even have to memorize these. These are on the formula sheet that I gave you earlier in the year. The mean is the same as the expected value, just like we talked about for discrete random variables earlier, and the standard deviation is the average difference from the mean. I'm going to show it to you in action here. For the example, there are 35% of all car-owning households that have 3 or more cars. You should remember this from earlier. I can figure this out very easily by saying, well, the number of trials is 400. They're independent trials. They have 2 disjoint outcomes. It's either 3 plus cars or they don't have 3 plus cars. And there's a fixed probability of success, which means 0.35. So I'm able to take the n and the p and multiply them together. That's 140. That's the expected value or the mean of the distribution. And the standard deviation of this distribution is just plugging numbers into a formula. No big deal. This is the practice question, which will round out our presentation for today. Remember the 15% of folks that were never married. We can do the same thing here, except it's asking for expected number or expected value. Remember that the expected value is the same as the mean of the distribution. So I'm multiplying n, which is the number of trials, times p, which is the probability of success. E of x is equal to 75, which means when we survey 500 adults, that's this number here, we expect that 75 of them have never married. All right, that was the second video in the 2-part video series about discrete random variables. This one's specifically about binomial random variables. Hope you have good luck with the Lumen assignment and good luck studying.